All right, in today's video, our goal is to discuss the ideal gas law and do some example problems with it. But before we jump to the ideal gas law, let's quickly review some other gas laws that we've already studied. The other gas laws are used when you have changing conditions. So if you're doing a problem and there's an initial pressure and then there's a new pressure, or there's an initial volume and then there's a new volume, or perhaps the temperature is changing. Those are problems where you would use these other gas laws that we've already studied. The other gas laws fall into two categories. They can either be a direct or an inverse proportion. Here are some things you need to know about those types of relationships. A direct proportion means that if you have two variables, let's suppose we're talking about variables A and B, then when A increases, B will also increase, and they'll increase by the same factor. So if A were to double, B will also double. On the other hand, if A were to get smaller, then the B would also get smaller by the same factor. So if A drops to 1/3 of its original value, B would also drop to 1/3 of its original value. So this describes what's called a direct proportion. Mathematically, you can say that A is equal to a constant times B. That's an equation for direct proportions. When you graph the two variables, if you were to make a graph of A versus B, if they're directly proportional, it'll create a straight line. When you look at this equation that we just wrote, A equals KB, it looks exactly like the equation from grade 9 math, Y equals MX, which is like a straight line. So therefore, a direct proportion of two variables A and B, if graphed, it gives you this straight line graph. When you rearrange the equation A equals K times B, you can say that A divided by B is constant. So when you have these variables directly proportional and you divide them, you'll always get the same answer, this constant, which means that if you have an A1 and you divide by a B1, so this could be, for example, an initial volume and an initial temperature, and you divide them, that will equal the A2, a new volume, for example, divided by a B2, a new temperature. So this is another algebraic way of thinking about direct proportions. Make sure that you know that a direct proportion can be described by this equation, A equals KB. Make sure you know that it produces a graph, which is linear, A versus B. And make sure that you know you get this type of relationship, A1 over B1 equals A2 over B2. Another type of relationship that we saw with these types of gas laws was the inverse relationship, the inverse proportion. And there, when one variable increased, if your A were to increase, the other variable would decrease by the same factor. So if A were to triple, the B would end up being 1/3 of its original value. Therefore, we get a different type of graph. When you graph the A versus the B, we don't get the straight line graph we saw before. This time we saw a curve that looked like this. We called the shape here a hyperbola. If you're a math student, you might object a little bit because technically that's just half of a hyperbola. It's the part of the hyperbola which is in the positive quadrant. In chemistry, all of our variables will be positive numbers, so this is the only part of the graph that we're interested in. When you have this type of equation, it means that the A, the first variable, is equal to a constant divided by B instead of multiplying by B. When you rearrange that, you can say that A times B gives you this constant. So the two variables, if multiplied, will always create the same answer, this constant. And that leads to an equation that looks like A1 times B1, which would equal an A2 times a B2. So again, for the inverse relationship, you should understand that you get a hyperbola when graphed, this curve. You should understand that the equation ends up being A is K over B, and that produces an equation like this: A1 times B1 equals A2 times B2. So now let's look at the specific gas laws that we studied. With Boyle's law, we actually did an experiment in class with a gas pressure sensor and a syringe full of gas. We noticed that when the volume was made bigger, when we pulled the plunger out, the pressure got smaller. So just right there, when the pressure was getting smaller, it was because the volume was getting bigger. So that tells us it was an inverse proportion. If it's an inverse proportion, then a graph of pressure versus volume would look like the hyperbola. And mathematically, it leads to P1 times V1 equals P2 times V2. And that's what most people would call Boyle's law. So you use Boyle's law if you're dealing with a problem where pressure and volume are changing. But the other variables, like temperature and moles, those would be held constant if you're doing a Boyle's law problem. With Charles's law, we noticed that when volumes increased, it was because temperature was also increasing. When you heat something up, the volume expands, it gets bigger. So when temperature goes up, volume also goes up. That means it's a direct relationship. If it's a direct relationship, then a graph of volume and temperature would look like the straight line that we saw with direct proportions. The equation that we get looks like this: V1 over T1 was equal to V2 over T2. All right, now here again, you would use Charles's law if you're doing a problem where volume and temperature are changing, but the other variables are being held constant. In Charles's law, temperature has to be the Kelvin temperature scale. Sometimes that's called the absolute temperature scale. So we have to use Kelvin temperatures because on the Kelvin scale, it starts at 0. The lowest possible temperature is 0 Kelvin. And all of the temperatures after that will be positive. So on the Kelvin temperature scale, there are no negative temperatures. That's why we use it in the gas law. We had a simple equation. You can calculate a Kelvin temperature by taking the Celsius temperature and adding 273.15. If your Celsius temperature is a whole number, like 25 degrees, then you can just add 273. If your Celsius temperature has decimal places, 25.3 for example, then you would include the decimals 273.15. All right? Now, sometimes pressure, volume, and temperature are changing in a problem. If all three of those are changing, that's usually called a combined gas law. It doesn't really fall into either of our categories because it involves more than two variables. If we take Boyle's law and Charles's law and put them together, we get this equation P1 times V1 over T1 equals P2 times V2 over T2. So there is the combined gas law. You use it when all three of the variables are changing, but the moles are held constant. Notice when you're using Charles's law or the combined law, or as we'll see in a moment, the Avogadro and Gay-Lussac's law, mathematically we solve problems using cross multiplication, right? So for example, if you say that 2/3 is equal to 4/6, you have an equation that looks like V1 over T1 equals V2 over T2. If you want to find one of those four numbers, if you want to find the 2, for example, if you cross multiply, you take the two numbers opposite, so the 3 times the 4, you multiply those, and you divide by the number that's by itself. So 3 times 4 is 12, divided by 6 gives you 2. So similarly, if you look up at Charles's law, if you wanted to find the volume number 1, you could say that V1 is equal to, let me just change my highlighter, V1 would be equal to T1 times V2, the two numbers opposite each other, divided by T2. When you're looking at the combined law, it's a little bit different, but not much. If you wanted to find, let's say you're looking for P2, then you would take the things that are opposite from each other, so you would take P1 times V1 and multiply by T2, so the things that are opposite you multiply, and then you would divide by everybody else. So you would divide by T1 and V2. So you might write there that P2 was P1 times V1 times T2, the things that are opposites, divided by the others that are there. So divided by the T1 times the V2. That's how you'd cross multiply to find P2 in the combined gas law. When you use Avogadro's law, it's because you're doing a problem where moles and volume are being changed while the temperature and the pressure are held constant. And here it's again a direct relationship, so it leads to an equation like N1 over V1 is N2 over V2. And again, our graph of N versus V would look like a straight line, and you might use cross multiplication to solve problems there. Gay-Lussac's law is where pressure and temperature are changing. It's also a direct relationship, so P1 over T1 would equal P2 over T2. A graph of P versus T would be linear, and when you solve this, you use cross multiplication. You always use Kelvin temperatures. While we always use Kelvin temperatures in these gas laws, the other variables, pressure, volume, and I guess moles, they can have different units. For example, you could use kilopascals for pressure number 1, as long as you use kilopascals for pressure number 2. You could use milliliters for volume number 1, as long as you use milliliters for volume number 2. You could use liters as long as you use it for both. For the moles, you could use moles, but you could use things like millimoles as well, as long as you used millimoles for both the initial and the final moles. But temperature has no choice. We always use Kelvin temperatures because we don't want to use negative temperatures in these equations. So those are the gas laws where variables are changing. One of the gas laws up above we called the combined gas law, but it really only had 3 of the 4 variables in it. There's another gas law which is really the true combined law because it has all 4 of the variables in it. Instead of just P1 times V1 over T1, it's actually P1 V1 over N1 times T1. So all 4 variables are now present, equals P2 times V2 over N2 times T2. I'm not sure why, but this gas law is not really used very often. But if you think about it, we can take this gas law and we can go backwards. If you remember, we found that A1 over B1 was equal to A2 over B2 because A divided by B was constant. So if we use the similar logic down here, if this is true, it must be because P times V over N times T is constant. So rather than just say that it equals K, the symbol we used before for constant, we're going to use a special symbol because here the constant involves all four of our variables. So we're going to give it a special symbol. We're going to call it R. It's just a constant like the other constants, but it involves all four of our variables: pressure, volume, moles, and temperature. It has a special name, this constant. It's called the ideal gas constant. Now, if you take that equation and rearrange it, you get what is commonly called the ideal gas law. P times V is equal to nRT. So all I did was take this R and I multiplied by the denominator NT, and that gave me nRT, and it equals P times V. So that's just a little bit of algebra to rearrange. This equation, the ideal gas law, is the most important gas law from grade 11 chemistry. Okay, if you forget all of the gas laws when you go to grade 12 chemistry, this is the one you want to hold on to. Okay? Now notice it has only one of each variable. Instead of a P1 and a P2, there's just P. Instead of V1 and V2, there's just V. So in this gas law, there are no changing conditions. You use the ideal gas law when there's only one set of conditions in the question. Only one pressure, only one volume, for example. Okay? The other gas laws are for where we have changing conditions. The ideal gas law is where the conditions are not changing. Now, because they're not changing and we have just one of each variable, the units are now kind of important. Before, we said we could use any pressure units as long as they were the same for P1 and P2. The same thing for volume. We could use any volume units up above as long as they were the same for V1 and V2. In the ideal gas law, we've only got one of each variable. So the units are now very important to remember. So let me change the color of my pen here. The temperature units, as always, have to be Kelvin. So we're always going to use Kelvin. The N stands for moles, and so, like it sounds, we're going to use moles. The volume, we're always, with the ideal gas law, we're going to use liters. Okay, that's the only volume unit we're going to use. If a question has a different volume unit, we're going to convert it to liters before we put it in. The pressure is where we have a bit of choice. We could, like the other units, always pick one and use it. But instead, I'm going to give you a choice. You can use atmospheres for pressure, or you can use kilopascals for pressure. Now, here's the catch. The R value is our constant, right? It's the ideal gas constant. Here's the catch. If we're using atmospheres for pressure, then the value for this constant R is going to be 0.0821. Okay, so when you use pressure in atmospheres, this is the value for R that you have to use. If you're going to use kilopascals for pressure in the ideal gas law, then now we use a different value for R. It's going to be 8.314. If you wanted, I could give you a third value for R if you wanted to use millimeters mercury as your pressure units, but we're not going to do that. If a question gave you millimeters mercury and you wanted to use the ideal gas law, you would choose one of these pressure units and you'd convert your millimeters mercury to either the atmospheres or the kPa. After converting your pressure units, you would choose the correct R value to use in the ideal gas law. So now let's take a look at a problem. Okay, so here we have a typical ideal gas law question. A propane tank, the kind you'd use on a barbecue at home, has 14 kilograms of propane. Its formula is C3H8 at 20 degrees Celsius. If the volume of our tank is 189 liters, what would be the pressure in atmospheres in the tank? So let's think about this. In this problem, it told us the mass of the propane, 14 kilograms, that's mass of propane. It told us the temperature, 20 degrees Celsius. It gave us a volume, 189 liters. And it's asking us to find pressure. So the thing we're trying to find is the pressure. This is what I want to know. Whoops, I just wrote T. This is a volume. All right, so in this problem, notice there are no changing conditions. There's no initial temperature and a new temperature. There's no initial pressure and a new pressure. There's just one of each. That's the clue to use the ideal gas law. So P times V is equal to nRT. We know the volume, and it's in liters. That's good. We know the temperature. It's in Celsius, so I'm going to have to convert that to Kelvin. The volume was given. The temperature was given. Do we know the moles? No, we don't. But the question did say we have 14 kilograms, and it said we have propane, which is C3H8. I'm pretty sure I can calculate moles. I can do that using either a unit multiplier. So, for example, we could say 14 kilograms of the propane. We could convert the kilograms to grams. Then, using its molar mass from the periodic table, we could switch grams to moles. So there's 1,000 grams in a kilogram, and the molar mass of C3H8, let me do some mental math, 3 times 12 is 36, plus another 8, this is going to be 44.11 grams. So this would give me the moles of propane that are in the tank. All right, if I grabbed a calculator, I could do that. But there's another way we could have done this, and that's what I'm going to do. I can change the moles in the ideal gas law to a different equation. So we have a simple equation for finding moles instead of using unit multipliers. Moles is equal to mass divided by the molar mass. So I'm going to take this and put it into the ideal gas law. P times V is equal to, instead of nRT, I'm going to say mass over molar mass times RT. So I just changed the moles to mass over molar mass because that gives me moles. So now I can rearrange my equation. If you're looking for pressure, we're going to have to get rid of this volume, which is multiplying the pressure. To get rid of something that's multiplying, you divide. So the pressure will be the mRT, the mass times R times T, divided by the molar mass times the volume. So there's a little bit of algebra. Now we can plug in our information. The mass was in kilograms. I do have to switch that to grams. 14 kilograms, if I look up above, I times it by 1,000. That means we actually have 14,000 grams of propane. The R value, the question said to give us the pressure in atmospheres. So if you remember, when you're using atmospheres for the ideal gas law, R is equal to this, 0.0821. So let's put that in, 0.0821. Our temperature, I'm going to do some mental math. You should show your work on paper if you're doing this for me. 20 degrees Celsius, I'm going to add 273.15 to that, and I'll round it off to 1 decimal. So that gives me 293.2 Kelvin. All right, just switch to Kelvin. Divided by our molar mass of propane, 44.11, and the volume has to be in liters, and it was up above 189 liters. We grab a calculator, 14,000 times 0.0821 times 293.2, and then notice in the denominator we have two numbers multiplied. So listen to how I type this on the calculator. Because they're multiplied on the bottom, I'm going to divide by the first number, 44.11, and then I'm going to divide again by the second number, 189. Dividing twice means I don't have to use brackets. So the answer I get with three significant digits, our volume has three digits, is 40.4, and that's our pressure. And because we used 0.0821 as the R value, this will be in atmospheres. All right, so the ideal gas law used when you have just one set of conditions. Let's do one more problem. A syringe holds 40 milliliters of hydrogen gas at 25 degrees, 102 kilopascals. How many molecules of hydrogen are in that syringe? So notice, again, we have one volume. It's in milliliters. That's a bit of a problem. We have one temperature. It's in Celsius. That's a bit of a problem. We have a pressure. It's in kilopascals. That's fine. We can use that. And then the question asks us for molecules. That's a little bit strange to me. Now, pressure, volume, and temperature, and we only know one of each. So I guess I'll write the ideal gas law, even though I'm not quite sure how that's going to give me molecules. But I know the pressure, I know the volume, I know the temperature. Well, when I look at that gas law, if I know the pressure, I know the volume, I know the temperature, and the R is just a constant, so I know R, then there's one thing I don't know. I don't know the moles. I want to find molecules, but I guess I can find moles, so why not do that? Using our algebra, to get the moles by itself, we have to move the RT to the other side. The RT is multiplying our moles, so to get rid of that, I'm going to divide by RT. So P times V will divide by RT. Because the RT was multiplying the moles, to get the moles by itself, we'll divide by the RT. You do the opposite of multiplying to get rid of it. Let's put our numbers in. The pressure was 102 kPa. There's nothing wrong with that. We can use that. The volume was 40 milliliters. So let me go up here and switch that. 40.0 milliliters. I have to use liters. So I'll switch it to liters with the unit multiplier. A liter has 1,000 milliliters. So on my calculator, that gives me 0.0400 liters. So there's our volume. If we're using kilopascals for the pressure, we learned earlier that when you're using kilopascals for pressure, the R value is 8.314. So let's go back here. The R value will be 8.314, and our temperature has to be in Kelvin, but it was 25 degrees. So I'm going to take 25 degrees and add 273. That gives me 298 Kelvin. Put that in here. And we can calculate the moles of hydrogen. That's not what we're looking for, but we can find it. So why not do this? 102 times 0.04 divided by 8.314 and divided again by 298. That gives me, I'm going to keep three digits in my answer, 0.00165 moles of hydrogen. We wanted molecules of hydrogen, but we know the moles. Well, that sounds familiar. In our stoichiometry unit, we know how to convert this. So let's set it up, a unit multiplier, 0.00165 moles of hydrogen. With a single multiplier, we can switch the moles to molecules of hydrogen, right? How do you do that? Well, we're going to use Avogadro, aren't we? 1 mole of anything is Avogadro's number, 6.022 times 10 to the 23 things. So in a mole of hydrogen, there's Avogadro's number of molecules of hydrogen. So grab my calculator, 0.00165 times 6.022. I use the scientific notation button to do the times 10 to the power of, and then type 23. That's going to give me a really big number, 9.64 times 10 to the power of 20 molecules of hydrogen. All right, so we used the ideal gas law to first find the moles. Why? Because we knew everything else in the equation except for the moles. So we found that. Once we found the moles, we started with it, and with 1 multiplier, we converted to molecules. So there's the ideal gas law. PV is equal to nRT. All right, it's the most important gas law from grade 11 chemistry. It's used when there are no changing conditions, when there's just one value for each of the variables, and the value for the constant R depends on the units for your pressure. If it's in atmospheres pressure, we use 0.0821. If the pressure's in kilopascals, R is 8.314. Temperature has to always be Kelvin, and our volume here has to be liters. That's the ideal gas law. Good luck.